Hi guys, this is Mrs. Allison. Today we are going to be talking about derivatives of exponentials and logs. But before we get into that, I would like you to do the quick warm-up. Just see how you do. It should take you about 2 minutes. Hit pause and then come back. All right, hopefully you'd had a chance to try each of these and to figure out what the answer is. So, hopefully we all got the same answer. So let's go through these. If we take the derivative of y with respect to x in this first one, what do we get? We get 0. It's just a constant. The derivative of constant is 0. In this second one, dy dx, what is the derivative? It too is 0. Because if we take the derivative of 4 pi to the 6th, that's just a constant. And the square root of natural log of 8 is also a constant. Okay, what about the third one? What'd you get the derivative? Well, if you recognize that this was a trig identity, you maybe got that y equals 1, and therefore dy dx would be 0. If you maybe didn't see that and saw a chain rule, and you got y equals sine squared, let's change that to dy dx, sine squared x plus cosine squared x, we'd have a chain rule, so we would have 2 times the sine of x, cos x, plus 2 times the cosine of x times negative sine of x. So then we get 2 sine x cos x minus 2 sine x cos x, which gives you 0. So the answer to this would be D. How'd you do? Okay, so let's go over our derivative of exponential and logarithmic function. So let's look at the rule first. One I'm going to give you and one we're going to look at how it operates. So the first one that you should know is that if I take the derivative with respect to x of a to the x, so a is the base, then x is the variable. If I take this derivative, this gives me a to the x natural log of a. We sometimes write the natural log first. It doesn't really matter. So a to the x times the natural log of a. That's the derivative for a to the x. So a couple of you asked about in class e to the x last week. So let's look at how we get e to the x. Because do you agree that this base a or this base e, they mean the same thing. E is a number, just like a is a number, raised to a variable exponent. So when I take this derivative, I would get the derivative of y with respect to x of this is e to the x natural log e, using the rule that we just wrote. Well, let's simplify that, because what is natural log of e? Well, the natural log of e is 1, so really this is e to the x times 1, so the derivative of e to the x is e to the x. Okay, let's rewrite that. Okay, so let's do the derivative with respect to x of 3 to the x. Try that one. Hopefully we got that this is 3 to the x natural log of 3. What if I were to take the second derivative of that one? Let's take the second derivative, or let's take the derivative with respect to x of 3 to the x natural log of 3. What would I get? Well, I would get from the 3 to the x part, this part right here, we would get 3 to the x natural log of 3, but then I'm multiplying by this constant, the natural log of 3. So we would get 3 to the x natural log of 3 squared. What about to the third power? What if I were to take the derivative of this to the third power? So what if I take the derivative with respect to x of 3 to the x natural log of 3 squared? Well, again, from the 3 to the x, we would get 3 to the x natural log of 3. And then this is just a constant, so we would have times the natural log of 3 to the third, sorry, that's a second, to the second. So my final answer would be 3 to the x natural log of 3 to the third. So my first derivative has natural log to the first power. My second derivative has natural log to the second power. My third derivative has natural log to the third power. Pretty cool. All right, let's look at our logarithmic derivatives. Okay, so the derivative of the natural log of x is 1 over x. Hopefully you remember that. All right, so let's look at the derivative of the log base b of x. So any log function that I could think of using the change of base formula. If you remember the change of base formula, using the idea that the log base b of x is really the same thing as saying the natural log of x over the natural log of b. We're using the change of base formula, essentially. So if I take the derivative of this, what I know is that for this first part, this natural log of x part right here, the derivative of that is 1 over x. But then I'm dividing it by a constant, the natural log of b. So if I divide by a constant, I'm just going to end up multiplying by 1 over that constant. And so therefore my derivative of log base b of x is 1 over x, the natural log of b. Okay. So let's try an example. If we have the derivative of log base 7 of x, I could rewrite this to say I'm looking to find the derivative of the natural log of x over the natural log of 7, which natural log of 7 is a constant. So I've got 1 over the natural log of 7 times 1 over x, which is the derivative of natural log of x, which gives me 1 over x natural log of 7. Okay. Questions on that? All right, let's keep going. Let's try to find some of these derivatives. I would love it if you'd hit pause and try these 4, and then come back and we'll see how you did. Actually, I think there's 5. Sorry. All right, let's go through these. If we take the derivative of y equals e to the 2x, you'll notice that there is a chain in there. So we're going to take the derivative, and we would do dy dx, x equals e to the 2x, but 2x was not part of the original, so that's my chain. And so this would give me 2e to the 2x. How'd you do? All right, try the next one. Y equals 2 to the cosine x. Hopefully you see the chain in there as well. So let's start with the derivative of 2 to some power. So the derivative of that is the 2 to that power times the natural log of the base, so natural log of 2. But then because I took the derivative, I've got that chain in there, so it'd be times the negative sine of x. And really there's not much simplifying other than that we can do. How'd you do? Okay, let's keep going. All right, notice in this next one that my main function is actually, the bigger function is something to the 7th power. So let's go and take the derivative of that. So we've got f prime of x equals 7 times the natural log of x to the 6th power. And then we would need to take the chain from the natural log, so we've got 1 over x. Probably would look a little bit different. We'd probably say the derivative of f prime of x is 7 natural log of x to the 6th over x. All right, next one's fun. If it helps you, you may want to rewrite this using the change of base. So what we have here from g of x is really the natural log of x to the 4th over the natural log of 5 using the change of base. And then when we do that, that natural log of 5 is just a constant. So if we take g prime of x, we get 1 over the natural log of 5 times, well, the derivative of natural log of x to the 4th is 1 over x to the 4th. But because x to the 4th, I would have to have a chain there, so I'm going to multiply that by 4x cubed. So a simplified answer would be, we would have 4 over x times the natural log of 5, because I can reduce
my x to the third and x to the fourth. All right. Finally, this fifth one, letter E. How'd you do? Well, we have talked several times about making functions simpler. This would be a prime example, but I'm guessing most of us, because we were talking about logs and exponentials, just looked at this and said, let's take the derivative. So we will take the derivative that way, and then let's look at the simplification. So if we use the rule, we would get that the derivative of y with respect to x would be e to this function, because that's the derivative of e to the x. And then we'd need to multiply it by 1 over x. But that requires you to remember, which would also help in the initial part, that e to the natural log of x is really just x. Let's call that x. So e to the natural log of x is just x. So then you have x times 1 over x, and x times 1 over x is just 1. So eventually you have to recognize that e to the natural log of x is just x. We could have done that in the beginning. Had I recognized that, then this problem would have just said y equals x, and we know that the derivative of y with respect to x of x is 1. So it may have been a little bit simpler than it looks. So sometimes we don't want to make things complicated just because they appear complicated. Okay, let's move on. All right, sometimes it will help to use our logarithm rules. Hopefully you remember some of those. We're going to look at them to be able to take derivatives of harder expressions. So let's look at our log rules and see if we remember them. Does anybody remember what the natural log of a times b, or log base b of a times b? Does anybody remember what we can do with this? Well, hopefully you remember that this is equivalent to the natural log of a plus the natural log of b. So, for example, if we happen to have something like the natural log of 3x, we could rewrite this to be the natural log of 3 plus the natural log of x. In that example, not very useful to rewrite, but sometimes it is useful to be able to rewrite it. So what about the natural log of a divided by b? Do you remember that rule? Well, that's the natural log of a minus the natural log of b. Natural log of a minus the natural log of b. So if, for example, I happen to have something like, and we can do this with log base. So if I had log base 5 of 3x over 4, I could rewrite this as log base 5 of 3x minus log, oops, that was supposed to say log base 5 of 4. Okay, last one. Anybody remember what we do here? Hopefully we remember that we bring this power down to the front. So we would have b times the natural log of a. B times the natural log of a. Probably one of the ones that most people get confused about, we're going to look at here in just a second, is remember that if I'm taking the natural log of 3x, let's rewrite that, natural log of the square root of 3x. Remember, I could rewrite this to be the natural log of 3x to the 1/2 power, and then the 1/2 comes down. So we'd have 1/2 natural log of 3x. I could then go on and simplify the natural log of 3x like we did in the first example. Okay, so let's try a couple where the problem looks more complicated, but it can be simplified a little bit more using our rules. Okay, hopefully you tried these and just gave it a go. So let's look at this first one. Hopefully you remember the rule we just talked about. So if I'm going to take the derivative of this, before I even take the derivative, I'm going to rewrite this to be the natural log of x squared plus 2x minus 3 to the 1/2 power, which means I'm going to rewrite it as y equals 1/2 times the natural log of x squared plus 2x minus 3.
So now when I take the derivative of this, I get dy dx equals 1/2, and the derivative of natural log is 1 over whatever the argument of the log was. So we get x squared plus 2x minus 3. But then I need to take the derivative of that, which is going to give me 2x plus 2. So we may see this simplified actually to be x plus 1 over x squared plus 2x minus 3 would be the derivative of y with respect to x. Okay, let's try another one. Again, using those logarithmic rules, the first thing I'm going to do is rewrite this problem. Oh, I don't even have a y equals. Whoops. We'll pretend it says y equals. So y equals, let's rewrite it using the idea that division in logs means subtraction, so the natural log of x plus 1. And then when I go to take the derivative of this with respect to x, I get 1 over 2x minus 1 times the derivative of that, times 2, minus 1 over the derivative of x plus 1 times the derivative of x plus 1, which is 1. So we would just get, simplifying, dy dx equals 2 over 2x minus 1 minus 1 over x plus 1. Okay, so it makes it look a lot simpler if we can use our derivative rules. Okay. But what about powers that don't fit in that power rule or exponential rule model? So let's look at a couple of examples and let's just review what the power rule is. So we know the power rule, that's the one we know really well, that the power rule says that the derivative would be n x to the n minus 1. And keep in mind, here, my base is a variable, but my exponent, my exponent is a number. That's different than the exponential rule, where my exponent is the power. Or I'm sorry, my exponent is power. My exponent is the variable, and my base is the number. Okay, so this one, when we're dealing with the exponential rule, this is the one we just talked about today, is a to the x times the natural log of x. Okay, so what about this craziness right here? If I take the derivative of x to the x power. Okay, so let's first look at a way to rewrite this, because we need an equation to be able to bring the exponent down or to deal with the exponent. So let's look at what that might look like. What if we rewrite this to say, let's let y equal x to the x. Then I'm going to take the natural log of y. I'm going to take the natural log on both sides. Oops, lost my pencil, move the paper. So we get the natural log of y equals the natural log of x to the x. Now the reason I would do that is because then I can bring the exponent down in front. So I get the natural log of y equals x times the natural log of x. Okay, now we're going to use a technique here that we're going to talk about more tomorrow that deals with taking derivatives. But remember, my goal here, as we can see from this notation says we're taking the derivative of y with respect to x. Okay, so when I take the derivative, I'm taking it with respect to x. So if I take the derivative, and this is called implicit differentiation, we'll talk about it tomorrow a little bit more specifically. If I take the derivative of all of this with respect to x, I know that when I take this derivative on the right-hand side, that'd be the left-hand side, when I take the derivative here, this would be 1 over y, but it would be dy dx. It was the derivative of y with respect to x. And on this left-hand, oh my goodness, I do know my right from my left. On this right-hand side, I would have to use the product rule here. So I would take the derivative of the first, which is 1 times the second, plus the derivative of the second times the first. And so we get this craziness that says 1 over y dy dx equals the natural log of x plus 1. Okay, well, I want to figure out what dy dx is. Remember, my whole goal is to figure out dy dx. So I'm going to undo it by multiplying both sides by y. So we get dy dx equals the natural log of x plus 1 times y. Now we can make a substitution back in for what y is, and so we get dy dx equals the natural log of x plus 1 times x to the x power. Okay, it's a little bit weird, but we're taking the derivative of y with respect to x, so that's the important thing to remember. So try it on this next example, which looks very similar. Try it on the next example and see how you do. Okay, hopefully you had a chance to go and think through this. So I'm going to let y equal x raised to the sine of x. And then I'm going to go through and take the natural log of both sides to bring my exponent back down. So then I've got the natural log of y equals the sine of x, natural log of x. And now I'm going to take the derivative with respect to x. That's the key, it's with respect to x. And when I do that, I get the derivative of natural log is 1 over y, but it was with respect to x, so I've got to put that in there, equals, and then I've got a product rule again, so the derivative of the first times the second plus the derivative of the second times the first. And then I'm going to multiply by y, so I get dy dx equals, and we'll do some simplifying in here, cosine x natural log of x plus sine of x over x times y. And then we get this craziness, dy dx equals the cosine of x natural log of x plus sine of x over x times y, which is x sine of x. And there's my answer. All right, you guys, so we will see some of you tomorrow, and your web assignment is 1.9. Have a good day.